This program is going to focus on the interplay between pOH, pH, and the ion constant Kw. In chemistry, we use P to represent a mathematical operator, which means the negative logarithm of. The reason we do that is it takes very small quantities and expresses them in a more manageable number. For instance, if we have the hydrogen ion concentration as 0.00015, well, you take the negative log of that, it allows us to simply write down the pH as 4.8, which we covered in the unit on pH measurements. pOH is the negative logarithm of the hydroxide ion concentration, and the equation here shown in red is in our IB data booklet. So if we're given the hydroxide concentration as 0.0067, we take the negative log of that number and we arrive at a pOH of 2.2, a more convenient number. We also need to be able to work in the other direction, and the equation shown here is not in our IB data booklet. It's sort of going the reverse of the first one, so we should remember it. So if we're given the pOH is 3, that means the hydroxide concentration is 10 to the negative 3, or 0.001. Let's look at a question now that involves the interplay of these three quantities. The pH of a near boiling salt solution is about 6.7. At that temperature, the ion constant for water is about 5.1 times 10 to the negative 13. I recall that the ion product for water is always equal to the H plus ion times the OH ion, no matter what the temperature. So I'm going to substitute in these values. So first of all, for Kw, 5.1 times 10 to the minus 3, and the hydrogen ion concentration is 10 to the negative 6.7. I'm going to turn that into a more manageable number. 10 to the negative 6.7 is equal to 2 times 10 to the minus 7. Now I can solve for the hydroxide ion concentration. Consulting again the IB data booklet, the equation to convert into pOH is the negative logarithm of that, and we arrive at 5.6. Is this solution acidic, basic, or neutral? The deciding factor is what the concentrations are of the hydrogen ion or hydronium ion and the OH concentration. Whichever is the larger allows me to determine what the solution is. In this case, I have the hydrogen ion concentration as 2 times 10 to the minus 7. That comes from this number. And the hydroxide ion concentration we determined as this number. Here I can clearly see that the hydroxide concentration is higher. Hence, this solution is basic. A special note here that pH equals 7, denoting the dividing line between acids and bases, which you might have been taught in previous science courses, only applies at 25 degrees Celsius and would have led to the long result in Part B. Thanks for watching.